So this is your fuzzy logic designer, and you have input is the fuzzification system, and this is the output which has the defuzzification system, and this is the rule system. So the input I can have it like, for example, let me say I'm building a very simple fuzzy system. So my first input variable is going to be age, right? So and what I see over here are different membership functions. So I can modify these. For example, the middle one, I wanted to make it as a trapezoidal membership function. So I make it over here. The parameters are over here, right? I can even play around with the parameters here. So it is, I want to be, and the range of this is from age, I'm going to put it from 0 to, say, 90. So you can see the range is modified here, right? And then let me say the age from 30 to 60 is middle-aged. Okay. So I hope you are able to view this. So there are two input variables, age and input 2 is my input 2 is weight. Right. Now my output function is going to be normal prone severe, right? That will be as it is, and I'm going to have a degree of 0 to 100. Okay. Now this is my rule section. So I don't know how clear the video is. So you can see my input variables here: age, weight, and disease intensity. Okay. So if my rules are going to be like, if my age is young and I am normal, right? My weight is also normal. The chances of me getting a disease is Now I am normal, then I have no disease intensity. So I'm going to add this rule, right? And my age, I'm a middle-aged person who's overweight. I'm prone to get this rule. I'm prone to get the disease. And I'm old and I'm overweight. Then I'm also prone to get the disease. Okay, I'm old, I'm obese. Then I'm in a very severe condition to get the disease. I'm old and I'm underweight. Then I'm normal. All these things are very trivial. Now, some extraordinary cases. You are young, okay, you are old, or you are obese, then you are always severe. So this is with OR operator, add rule. And you are old, okay, or you are old, or okay, you are young and you are obese. Then you are okay. So these are some of the rules. Just imagine, right? So how did I get the rules now? Can you tell me? How did I put these rules? Or you too can put these rules, right? What am I trying to predict? Some heart disease or some disease based on age and body weight. So age and body weight, we all can do the system. We all know what the system is. So I gave some rules for the system, right? You know that how my parameters are set for both the input variables. You have now known how I did the triangular mapping, all that fuzzification, all that stuff. If suppose age is 30, how do I put that? Someone comes in 29, he comes into the next group also. All this is fine. Now this is my rule-based rules. From where did I get these rules? Experience. Yeah, great. General knowledge, experience. So I am a doctor here, right? At least as of now, for now. Not doctorate, the original doctor. In general, fuzzy systems has two people in the design. One is the knowledge engineer, another is the domain expert. So here, the knowledge engineer is me who is building the system, and the domain expert is supposed to be the medical diagnosis person, or the doctor or the expert in the domain. So he is going to give me the rules. Okay, this is what, this is how it will be, that is what it will be, and so on and so forth. And he is the one who's going to tell me that, okay, age can be young, middle-aged, and old. No, no. Temperature can be very low, normal, medium, high, and very high. So all these parameters of the fuzzy system is going to be given to you by the domain expert, and the knowledge engineer who is building the system is going to only operate on the system, right? And he's going to look into the operational feasibilities and the efficiencies of the system. We'll come to that a little later, how the system will be efficient and feasible and all these things, okay? So now I'm done with the rule inferencing part. Fuzzification, rule-based system or rule inferencing, and then the final one is defuzzification. I have not yet come to the defuzzification part. So this connection which you see over here, or a RAND, is the aggregation, or the aggregation part that you see over here. Okay, done. Okay. Now this is your system. For ease of understanding, I will keep all the variables in the OR type. Uh, okay. Now see, suppose my age is 16. My age is 16, and my weight is, say, 50. Okay. So what is my general intuition? Age is 15, young age, and weight is 49, somewhat in the middle, and disease intensity is, if I'm young age and weight is 49, what is the first rule? If age is young and weight is normal, disease is going to be normal. That is what has happened over here. First rule is fired, right? So this rule, now come to the second rule. I am 16 and this is my age. So if you see 16 here, 16 will be more towards mid, right? 16 will be more towards mid, and 16 and weight is 49, but my weight is 49 is fine. But what is the second rule? Weight is overweight. So this overweight is going to be used here, but this weight does not contribute anything to this, right? So I am least bothered about the outcome of this, right? So that's why I said I'll make this as R. Age is 11, weight is 90, and so now see, age is 11, its membership value with young, come over here. If age is 11, its membership value with young is going to be high, right? And weight is 90. So 90 is membership value of 90 with normal is going to be somewhat normal, if you remember, right? It's not completely normal. It is the end of normal, right? So normal. What do I say? What does the rule say? What will be the disease intensity? 11 years fellow, his age is normal. If age is normal, then his rule says his intensity, the disease intensity is normal. This is for normal. How much normal? What is the degree with which it is normal? It is the maximum of these two. Why it is maximum of the age and weight? If it is 0.19 here and 0.6 here, it's going to be 0.9 normal intensity. Why it is 0.9? Because R means maximum. Any doubts about the first rule interpretation? Right? So now coming to the second rule. If age is middle age and if the weight is overweight, then disease is disease prone. So what do I see here? Age 11 is somewhat towards middle age. Don't consider this very strictly. Just see from a system perspective. So his association with middle age. Generally, we tend to have 25 years middle age, but 11, it's not a kid. It's okay. Let me take it as so. His association is something 0.2 with middle aged, right? But his weight for 11 years of age, his weight is see this. Weight is overweight. So and for 11 years, 90 kgs overweight is some 0.6 or something. For 11 years, 90 kg is too much, right? So this rule says his intensity, he is more prone to the disease. So you can see here, his value to prone will be point what? 0.6 or 7, which is contributed by the weight variable. Able to understand the second interpretation? How many yeses, how many no's? If anybody is no here, please stop me here. At the end, if you ask me, I cannot come all the way back. Why it is no, why it isn't and, right? Okay. Let me come for the same criterion, why all these blanks are empty. Okay. So here, these rule says, let me take this rule, for example, fifth or sixth rule. Age is old, weight is obese. Doesn't come in any of the categories. Fine. Age is 11, so this old is set over here. It is not, has no membership value with the set, and set is obese, and so on. All these belong to old, right? So let me have one more mid age. Mid age, and then weight is normal or mid age, overweight. Then he is severe. Okay, let me add this new rule. Okay. See now, the same thing. Mid-age, middle-age, middle-age and overweight. This is prone. Eighth rule, middle-aged, overweight and severe. How much severe? How much severe? If this is 0.6 and if this is 0.8, able to see my cursor. If this is 0.6 and if this is 0.8, this will be 0.8 here on the intensity part. Likewise here, if this is for rule 2, if this is 0.6 and this is 0.4, this will be 0.6 over here for less intensity, prone intensity. Okay. So all these are OR operators. If you have it as an AND operator, let me update this rule. I'm updating rule number 8 now and making to AND. You can see over here. Add rule, change rule. Now you see the difference. What's happening? The minimum of these two is taken. The minimum of these two is taken if you take it for a conjunction. If you take it as a disjunction, it's take the maximum. Right? Okay. Now, what do I infer from this? What is the advantage of, where is this uncertainty handling, modeling, reasoning? Where is all this drama? The first part, you have done a good amount of uncertainty handling by putting a proper fuzzification function in your input variable. This is similar to discretization here. Age has been discretized into 3 sets. Weight has been discretized into 4 sets. And disease intensity has been discretized into 3 sets. So the aspect how you have discretized and modeled the characterization or the working of those discretization functions, whereby I call the fuzzy sets, are characterized by the membership functions. So how we have modeled the working of the discretization function is where you call as fuzzification, right? So you have done that, and at that stage itself, some amount of fuzzification is handled. And now coming to the reasoning part, if this is going to be a simple crisp system, imagine this rule view is not there. This entire rule view is not there. And take this case, 14 years and 96 age, 96 kgs weight. 14 years and 96 kgs. So what will a crisp rule system do? If it's going to be a decision tree, 14 and 96. 14 is young age, 96 is, where is my chart? 14 is young age and 96 will be overweight, right? So my rule system will say 14 and overweight is prone. That's all. No. 14 and overweight. Is there any rule for that? See here. Young age and overweight. Now that is the criterion. Is there any rule for young and overweight? First one is young and normal. Mid and normal. No young here. So young and obese. So I have only two rules for young and obese and young and normal. There is no rule for young and overweight at all. So if I have a crisp system, if a person is going to come to me for young and overweighted person, I don't have a rule to classify him at all. Able to appreciate the use of the system now. This is my rule-based system. Don't think of the human way of reasoning. Just imagine this, you are giving a test instance. Young, overweight. What will be my disease? I'm testing with rule number 1. Young and overweight, young and normal, doesn't match. Second one, mid and overweight, doesn't match. Yeah, old. Young and obese, doesn't match. So young and overweight, no rule matches. So I can give a default rule like no disease, or I can go for other rule matching patterns like partial rule matching, like okay, if it's young and then the next thing we discard what is young, and so we can go for partial rule based matching classifiers or associative classification approaches which have partial rule matching. Again, that is a different area of classification. So as of the strict system, when I come to young, whatever, I consider a decision tree, young. If it is young, next attribute I am taking is weight, right? Using age is young, so it's going to go to young. And in young, I have no node for weight, so it's going to go to some default with a mistake. That is what a decision tree does. Yes, you know that the confidence factor and all that we set in the decision tree. If it is beyond some confidence level, we are going to put it into some default class. Now, but what does this fuzzy system do? If he's young, okay. If he's middle-aged also, that age of 11 is not strictly young alone. It has some association with middle-aged. It has some association with middle-aged. So I cannot take young to be 11 years or leave 11. Let me go to 16 or 18. So this kind of partial situations. So in this kind of partial situations, your human reasoning is not going to stop working with only two rules. Rather, you are going to reason out. Okay, if it is 11, okay, but his weight is too much, 90. Just because there is no rule for young age, you cannot rule out that person and say he will not get the disease. Or just because this person is young age, you cannot say that he will never get a thing because his weight is more. And you cannot completely go by crisp rule-based systems. You need to look into all kinds of uncertainties that are in the data, right? So this is the kind of uncertainty modeling, the uncertainty in the data, so that you can make some inferences out of this. Able to appreciate the use of fuzzy inference system. Now, where to get the data, what is the process, where to get these rules, where do I use GA? This is where the crux of the project is all about. Okay. So now I'm going to give you the heart disease data set or whatever data set you want. Now, where do I get the data set from? Any repository, Kaggle, UCI, Keel data sets. There are so many n number of data sets, right? And you have a good description about the data set. Now, you have got one data. This data is continuous. Some variables may be continuous, some variables may be categorical. Leave the categorical. You take the continuous variables. You are going to discretize it, right? Now, my hard data set had continuous variables. What are the continuous variables? The thing that I showed you here, age and weight, are continuous variables, and I discretized it, right? I discretized it, and I had the class attribute, that is disease intensity 0 to 100. That also I discretized it, right? So after I discretized the same data set, I'll get in a discretized form. How will I discretize? What are the methods I have for discretization? Equi-width, equi-frequency, binning, smooth binnings, hard binnings, median-based binnings. So many approaches are there, right? So you can use any one of the approaches, and you can take how many ever bins you want for each of your variables. It may differ, right? Fine. continuous attributes you have binned. So you are now ready with a set of continuous weight data, a set of discretized data, right? Now this discretized data, rather I'll draw a flow diagram so that you will not come back again. Okay. So I have a data, 1,000 patients records, whatever records you may have, discretize. You have the same discretized data for all the continuous variables alone in the data, right? Now, this discretized data, you are going to give it to some machine learning algorithm, decision tree, random forest, or even some rule-based algorithms for which you already have packages, partial trees or random forest or XGBoost or whatever. Some rule-based algorithms from where you can get the rules. Okay. I hope you are clear with this step. What will be the outcome of this? What will you get? You are giving discretized data to a decision tree. What will you get? You will get a decision model, a tree, or a set of rules, right? You will get a decision tree, or you can extract rules from the tree. Got it? Now coming to, now you have the rules. Remember, now this I call it as rule set. Remember this. And how will these rules look? How will these rules look? Young, obese, severe. Am I right? Because what is the data you have given? This is the data you have given. So your rules will look of this format. Clear? Process is clear till here. Fine. Now go into development of fuzzy inference system. Input variables. What are the input variables? Let me name it as capital D. And this is D discretized. What will be the input variables for the fuzzy inference system? Each and every attributes of D. Right? Each and every attribute of D in its continuous form. So there you are going to give the discretization. What discretization are you going to follow? The same model that you applied over here. The same discretization model you opted here, you are going to opt it for this fuzzy inference system. Right? Now, what do you need in the fuzzy system? You need rules. So, where will the rules come? There's no need of an expert here now. You got the rules from the tree. Right? And you're going to, what will be the output? In what format will it be? You can get it either in linguistic format. By linguistic, I mean severe, that also is available, or if you defuzzify it, you will get the crisp value also. The same output value which you have in your original data set also you will be able to get. Able to map the complete flow. Discretization, machine learning, inferencing, everything is fine now. Now where is this GA? Where all can I apply GA? Where all do I need an optimization in this part? Or what are the parameters in this system that I can optimize? There are so many. One, the number of attributes at this point of a time. So I can use GA here, select a subset of attributes, right? There are two ways of using GA here. or attribute selection, as I told you before, can be done in two ways. This entire model can be brought into the selection part. What did I tell you there? Filter based attribute selection and wrapper based method. Did I discuss in the class or not? Filter methods and wrapper methods of attribute selection. Filter is, if I have 10 attributes, I'll say more than information gain or more than chi-square, I'm going to select those attributes, and the rest of the attributes I'm going to remove from the data, and right from the initial point itself, the data, both the data D and DD are going to have only those attributes. Done. If it's going to be the wrapper, I'm going to use some set of attributes, go to the GA, that GA is going to set a subset of attributes, give that data set alone, and that data set is going to have that subset of attributes, run this entire structure, take the output, now take another set of attributes. This entire structure is what? The fitness function of your GA. Able to correlate? GA tells 110011. That means first, second, and third, and 10th and 11th attribute. Right. Now that 1, 2, 3, 10, 11 is going to constitute my data set. Middle columns are removed from the data set. Using that data, I'm going to create a decision tree. Using that decision tree, I'm going to get a subset of rules. So if I have 100 attributes, just imagine how my rules will look here. 100 attributes will give so many rules. Each rule will be so long. But if you have 10 attributes that are really efficient, then you assume how less complex your system would be. So GA, the picture of GA for attribute selection comes over here. GA can be used for the first point for attribute selection. The second part where you can apply GA, I'm not telling you to do everything. You have to implement GA, but use GA for any one purpose, either for attribute selection or, now leave attribute selection. Let's come to rule set selection. If you have 100 rules generated by the decision tree algorithm, is it necessary that all the 100 rules should be encoded into your fuzzy system? No, right? Out of the 100, you need not take 2 long rules that may overfit the situation. You need not take 2 short rules that may generalize too much. You may take some subset of rules that are more capable of representing the situation. So how do I know which is a good subset again? That is another complete different area. Rule set evaluation. If you want, you can ask, look into one of my papers, knowledge-based evaluation, that has many rule support measures for evaluating the goodness of a rule subset. Right? So how many, the one rule, how many data it covers, what is the support of each rule, what is the confidence of each rule, that is rule interestingness measures for support, and that is a different area. But if you have no idea about all these measures, just take a GA, put some subset of rules, see how good the fuzzy inference system is going to work, take another subset of rules, put it into a fuzzy inference system, see how good it is going to work. You need not work in the initial framework, right? You have to work on only on this half of the system. You need to work iteratively only on this half, focusing on the rule base. Take 20 to 30 rules, put it into the FIS, see how efficient your FIS is, what is the error rate of its FIS, data set still remains the same. So that is another application of GA. Now the third application of GA. You have so many parameters in your fuzzy inference system. What are the parameters? How many membership functions should I use? What will be the values of my membership function? The doctor says there are 3 sets and the set value should be 30, 35. That's one doctor will say 30, 35. Another doctor will say 40, 48. What is the best parameter for a fuzzy inference system? As a knowledge engineer, how am I supposed to know how many sets should be there in age or how many sets should be there in temperature? I don't know anything about your domain. So as a knowledge engineer, I'll just form a GA. I'll just put an optimization algorithm and let it run for some 200 runs and let it take some random variables, try, test, train, try, test, and train. And finally, it will come up to some value somewhere. It is going to fit in and say, okay, this gives a good optimal results. For this set of attributes, this set of rules, these parameters are what is going to be good. Now here, a binary representation would not work. If you are going to represent the values of a triangle fuzzy system, then it is important to design each and every individual in your GA. How you design the solution, right? That's not going to be a simple 1010 solution. You have to hard code the values, and for that you need to take an appropriate crossover. Simply giving a GA that your Python package gives will not optimize your fuzzy system. Never. Okay. So, able to get this entire project